Welcome to lecture number 4 of the series on basic mechanics, a critical look. Over the past few lectures, we have been taking a deep look at Newton's laws. We have seen that Newton's first law sets the stage for the use of Newton's second law. If you want to use Newton's second law, you must make sure that the observer whose observations are being used to calculate the acceleration is an inertial observer, that is, an observer for whom Newton's first law works. So we can definitely say that Newton's first law defines an inertial observer. But that is not the full impact of Newton's first law. What we saw in the last lecture is that the real meaning of Newton's first law is that it states that inertial observers exist. Its importance is as an existence statement for the concept of inertial observers. Once you use Newton's first law to figure out one inertial observer, you can, of course, then find infinitely many. But finding out the first inertial observer and the fact that you can at all do that, that is the critical input which comes from Newton's first law. But that is not all. There is a lot more. In fact, we stated at the very end of the last lecture that Newton's first law helps us to, at least at the physicist level, define something which has been rather mysterious throughout human history: time. To understand what is problematic about time and how, in the end, Newton's first law at least gives us a physicist's way of handling this issue, let us first begin with this very simple concept. Time, of course, is central in mechanics. When you say things like velocity, acceleration, and so on, these are rates at which position vectors change with time, or the rates of change changes with time. So without time, we cannot talk about mechanics. But the important point is, how do we measure time? Let us contrast this with the measurement of something equally fundamental, that of length. Suppose we have two 1 meter rods. Let's say like these two rods you can see on your screen right now. Can we actually compare whether they are equal in length? Of course we can. All we have to do is pick one up, put it right next to the other, and check whether they match up end to end. So, comparing the lengths of two 1 meter rods and deciding whether they are equal or not is simple. You just take the rigid body representing the rod, move it to a new location. But just think about it a bit. You cannot do the same thing with time. How can one tell whether two 1 hour intervals are of the same size? Let's say the interval between 12 noon and 1 p.m. Is it equal to the interval between, say, 2 p.m. and 3 p.m.? Depending on how alert you are, how sleepy you feel, one may seem much shorter than the other. But of course, we are not talking about human feelings or perception here. We are talking about things which can actually measure. We cannot pick up the 1 hour interval between 12 noon and 1 p.m. and place it next to the 1 hour interval between 2 p.m. and 3 p.m. and compare the two. That, of course, is out of the question. How then do we make sure that the two time intervals are actually equal? Now, at first glance, this may seem like a very silly question to ask. After all, we do have clocks. All we have to do is to take a look at the minute hand of a clock and see whether it goes all the way round. It should go all the way round between 12 noon and 1 p.m. and again between 2 p.m. and 3 p.m. And that should tell us, because the clock hand rotates at a regular speed, that these two 1 hour intervals are actually the same. But think about it a bit. How do I know that the clock hand really rotates at a regular speed? And indeed, if there were more than one of us and we were using different clocks and the clocks did not agree, how does one decide whether one clock is better than the other? After all, clocks have evolved over the years. The clocks that we used in the yesteryears are deemed to be too inaccurate for precise work now. Today we use atomic clocks which are supposedly better than other clocks. But how do we know that the atomic clocks are really better? Couldn't it be that the atomic clocks are actually worse than the other clocks? And that is why the two are differing in their readings? To emphasize this point a bit more, let us take a look at a scenario where we describe time measurements by 4 different friends or frenemies of 4 events. The events we are calling start, A, B and C. These could be 4 laps of a long distance race. And our first friend, called Amar, sees that these events occur at time 0 according to his clock, then time 50, let's say 50 seconds, then 100 seconds, then 150 seconds. So these are Amar's readings or Amar's clock's readings for times at which these events occur. Akbar, on the other hand, agrees with Amar that the start event occurred at 0, but his readings differ for the other events. They are 55, 110 and 165 respectively. And then his clock is even worse. Or, as we just said, we don't really know it's worse, but it's different definitely. At start it shows 0, at event A it shows 60, at event B it shows 115, at event C it shows 165. And we have this fourth person, Robert, whose readings for the same, given though that all 4 friends have recorded different times for the events, except of course for the starting one, how can we really be sure that it's Anthony's clock which is erratic and not those of the other 3? Now you might be inclined to vote in favor of the other 3 because their readings are in some sense consistent with each other. That is, they're just shifted or scaled versions of each other. And Anthony's version is of course much more complicated. But physics is not really decided by democracy. Just because 3 people's clocks agree and the other ones doesn't, does not really mean that the 4th one is necessarily worse off. After all, an atomic clock will give readings which do not agree with any of the other physical clocks that we use. But what really helps us to decide that the atomic clock is better? How can we be sure that here is Anthony's clock which was faster to begin with and then it's slowing down, and not the fact that the other clocks had been slower to begin with and are now speeding up? Now the answer to this, and to the general question of what makes one clock better than the other, can be answered, at least in physicist terms, via a rather famous quote by Kip Thorne. Time is what makes motion simple. Let me now explain what this quote really means by appealing to what else? Newton's first law. In the previous lectures, we had seen examples of measurements made by different observers. We had actually taken a look at 2 observers who were moving with respect to each other, O and O prime. They measured different position vectors for the same particle, and although they were using the same time, this might lead them to measure different velocities or different accelerations. But let us now focus on a different scenario. Let's say O and O prime are 2 observers who share the same origin, so they measure the same position vector r for a given particle, but they use 2 different time measurements, t and t prime. Now, t and t prime should both have this monotonicity feature, that is, things should occur only forward in time and not backward in time. So t prime could be some arbitrary complicated function of t, but it has to be a monotone function. As time elapses, so to speak, the variable t should increase, so should t prime. Now, given this backdrop, let us try to calculate what velocities or accelerations the two observers will measure. They measure the same r but use different t. So, the first observer, O, will measure the velocity of a particle to be dr vector dt, where r vector is the position vector of that particle, and t is of course the time which O is using. But using a chain rule, what we can do is rewrite this derivative as dr dt prime times dt prime dt. And note, here r is the position vector of the same particle also with respect to O prime. T prime is the time that O prime uses, so this is the velocity v prime measured by the observer O prime. So here you see that despite using the same position vector, same origin, hence same position vector, two observers differ according to the value of the velocity of a point particle. They are related by a factor which is given by essentially the relative rate of the two clocks, dt prime dt. But things get even more complicated when we go one step further and look at the acceleration. Now, if you want to find the acceleration with respect to O, you have to differentiate the velocity with respect to time. So you do a ddt of this expression. I'm actually trying to relate the acceleration as measured by O to the acceleration as measured by O prime, where, of course, dv prime dt will not be the acceleration, dv prime dt prime will be the acceleration. But notice that what we have done in this step is simply opened up this derivative of a product into two factors, standard Leibniz rule. Derivative of v prime times dt prime dt breaks up into two terms. One in which v prime is being differentiated with respect to t, other one doesn't change, and the other where v prime stays intact, you do a derivative on the second term. But now what we need to do is rewrite this to get the acceleration a prime, which means dv prime dt prime. So I have to use chain rule again, and we will end up with this result. dv dt is dv prime dt prime times dt prime dt whole square. One more factor of dt prime dt has come in because of the use of the chain rule. Plus, of course, the second term v prime into d2 t prime dt2. Or, the acceleration as measured by O is related to the acceleration as measured by O prime and the velocity as measured by O prime through this equation. A rather complicated looking equation. So just the fact that two observers use different measures of time can lead to very complicated relationships between their measured accelerations. Now let's specialize to the situation where the observer O is inertial. Newton's first law really works for him or her. Therefore, if the observer O is looking at a point object which is force-free, the acceleration A should turn out to be zero. That is Newton's first law. However, in this case A prime, the acceleration as measured by O prime will turn out not to be zero, but to be given by this rather complicated looking expression. It's going to be negative of d2t prime dt2 over dt prime dt whole square times the velocity as measured by O prime. So, if the object is at rest with respect to O, then it stays at rest with respect to O prime, v prime being simply proportional to v, so v equal to 0 would mean v prime is also 0, and then A prime would also be 0. But however, if you want Newton's first law to hold for all force-free objects, that is, you want it to hold as long as the object which is force-free turns out not to accelerate, but could also possibly move, then you have the following. Newton's first law will not in general work for O prime unless you have d2t prime dt2 equals 0, and that means t prime has to be equal to a constant times t plus another constant. T prime has to be at plus b. So if you have two different inertial observers who share the same origin, or even if they don't share the same origin, they might very well get away with using different times. T prime and t do not have to be identical. But the most they can differ by is by a shift, the constant b in the expression at plus b equals t prime, and the scaling, the factor a. So in our example of the friends before, if Amar happened to be inertial, so actually would Akbar be, because Akbar's times are only rescaled versions of Amar's times. Robert would also be inertial because his measurements are just shifted versions of Amar's times. Anthony, on the other hand, would not be an inertial observer if Amar was one. So Newton's first law actually restricts what a good clock should be. If you are using a good clock, a force-free object should end up being acceleration-free. If you use a bad clock, one which does not run at a uniform rate with respect to the clock of an inertial observer, then you will not be in a position to use Newton's first law, and hence you will not be inertial. Also, a moment's thought should convince you that while I have stated everything here in terms of two observers who share the same origin, a very similar thing can also be said about two observers who are translating with respect to each other. Basically, it's the same kind of calculation that we had done in a previous lecture, where, of course, the position vector of the point P, as measured by two observers marked O and O prime, are going to be different vectors, R and R prime, whose difference is going to be given by this relative position vector of O prime with respect to O, which is something which you have called capital R. And then, if you differentiate this thing with respect to T, this is what follows. But now we have to realize that this term is no longer the velocity of the point P with respect to the observer O prime, because O prime is now not only moving with respect to O, it's also using a different time, T prime. And therefore, the correct formula relating the two velocities in this case would be V, which is this term here, equals V prime times dt prime dt. That's the chain ruler action here. Plus this term, which is of course the velocity of the observer O prime as measured by observer O, which is why the derivative is with respect to time used by observer O. Now, one more differentiation with respect to T, and we are going to get acceleration connections. You are going to get dv dt is ddt of this term plus ddt of this. Now this, of course, is the acceleration of the observer O prime as observed by observer O. So that's the term A obs here. This term, once again, as in the previous case, splits into two pieces. And so finally, once you put them all together, you get this generalization of the result that we had obtained before. The major difference now is basically twofold. One is you now have an A observer, which you did not have before. Because earlier, remember, the consideration that we were talking about was a situation where capital R was always 0, so its derivative and second derivative were also 0. The other important thing is, even if V is 0, V prime will not be 0 in this case, because now the presence of the V observer tells you that V and V prime are no longer proportional to each other. So that's also a difference from our previous situation. But the situation that we are most interested in, suppose observer O is actually an inertial observer. So it does see a force-free object to be acceleration-free. So for a force-free object, A is 0. Now, we already know that if O prime accelerates with respect to O, and O is inertial, then O prime cannot be. But even if A ops is 0, that is, even if O prime would have been inertial otherwise, is translating with a constant velocity with respect to O, even then, A prime would not be 0 in general. Unless, of course, this term vanished. For a force-free object, of course, A is 0, so this term is already 0. A observer is 0 by supposition. We are talking of observer O prime translating with uniform velocity with respect to O. But now this means that these two terms have to add up to 0. So only way A prime is forced to be 0 in this case is if this term vanishes. And that happens, as before, when T prime is a scaled and shifted version of T. If this relation exists between the times as used by two different observers, the same relation we found for the special case before, then and only then would an observer who is not accelerating with respect to an inertial observer also be inertial. It's not just the state of motion of the observer which is important here, but also time he or she uses. But now it seems like we have actually solved the problem of what time to use. Take the time a non-inertial observer uses, and the most general possible time another inertial observer can use would simply be a scaled shifted version, and that is all. So, if you have found the time that one inertial observer uses, all other times fall in place. The maximum that you can do after that is scale up the time, which is essentially use a different unit for time, and shift it, which is essentially just use a different origin for time. So it seems that the problem has been completely settled. But this situation is actually very similar to where we were in the last lecture as well, when we were talking about inertial observers. Remember, there we were using observers who are both using the same time, and we said that if one observer is inertial and another observer doesn't accelerate with respect to that observer, then the second observer would also be inertial. The thing that we are adding to that here is, if one observer is inertial and a second observer does not accelerate with respect to that observer, and in addition uses a time which differs from the first observer's time only by a scaling and a shift, then the second observer is also inertial. So, if you found one inertial observer and his or her time measurements, you have essentially found all inertial observers and their time measurements. But the problem, as in the previous case, is how do we find the time that the first inertial observer uses? In other words, how can we define time in such a way that at least for one observer, Newton's first law will be valid? Once we answer that question, the rest is straightforward. But the problem, let me emphasize once again, is finding out the time as used by our first inertial observer. We need a case 0 from which we can proceed. We settled that point in the previous lecture by saying, let us fix an observer with respect to a distant star. And then we have ensured that a force-free object, namely the distant star, does not accelerate with respect to this observer simply because that object, in this case a star, is stationary with respect to our observer. But we then went on to say that Newton's first law does not tell you the trivial things that such an observer will see your distant star to be acceleration free. That is trivial from the way you have defined this observer. However, it also goes on to say something much deeper about the universe, which is that once you have found such an observer, all distant stars will not accelerate with respect to that observer. In other words, the deep statement that we made was inertial observers exist. something which is not obvious from the definitions involved. Let us now argue along similar lines to show how Newton's first law can actually help you not only figure out the first inertial observer, but also figure out the notion of time which this inertial observer must use. Remember, our first inertial observer is one who is fixed with respect to a given distant star. Of course, that particular distant star will not move with respect to this observer, and that will not really be very useful for the purpose of defining time. For that, what you need to do is use this same observer, but observe a different distant star, one which is moving in the frame of this observer. Now, one thing Newton's first law guarantees for you is that this motion of the distant star will be along a straight line. And now what you will do is the following. You will consider 3 points A, B and C on the path of the distant star. This distant star which is moving with respect to our chosen inertial observer. And you choose these points in such a way that the distance between A and B and that between B and C are equal. Now, we have only stated this for 3 points here, but you can easily extend this argument to more and more points. All you need are equally spaced points on the path of a particular distant star. And now, what you will do is the following. You will assign some value, let's say capital T, to the time when our star is at A. When it moves to B, then you will say that the time for that particular event is capital T plus tau. So you are saying a time of tau has elapsed in which the star has moved from A to B. That in itself would be trivial, but what you then say is that when the star moves from B to C, which remember is the same distance as before, the time interval is exactly the same. The time you assign to the point C or the event which is occurring at C is capital T plus twice tau. And of course, if you had more points D, E, F which are all equally distant from each other, then our time measurements would be T plus 3 tau, T plus 4 tau and so on. So what we are doing is we are using this distant star to establish our notion of time. Now once you have done that, it's obvious that if you use this notion of time, the star is traveling equal distances at each of these intervals in equal time intervals. No magic there, though that equal time interval is here by definition of the time that we have put in. In other words, this particular distance star will definitely move with a fixed speed, and because it's moving along a straight line, hence a fixed velocity as well. As a result, this distant star will not accelerate with respect to our observer. Note that the original distant star with respect to whom we fixed this observer will simply not accelerate because it's not moving, but this one, the second distant star, will be moving but yet not accelerate. But this is really rather trivial. All you are saying here is that the acceleration will not be there because this is how we have defined our time. In other words, if this were all there is to it, Newton's first law would simply look like a trivial matter of defining time properly. And again, this would render Newton's first law non-physical. It would just be a matter of definition. However, this would be the case, and it would have been completely trivial had the universe only one such distant star. Of course, I say one here, but I really mean two. The first one with respect to whom we have fixed our observer to render him or her inertial, And the second one has been used to define time for us. If these two were the only stars in the universe, then force-free objects or acceleration-free would not be a profound statement. It would simply be a statement about how you are defining time. But the universe does not have only two distant stars. It has more. And that is where the whole impact of the first law lies. Along with our reference star, which we are calling S1 now, let us consider another star S2. When star S1 is at A, star S2 is located at A prime. At the instant when S1 is at B, S2 will be at B prime, some position. When S1 is at C, S2 will be at another position, C prime. Once again, Newton's first law already guarantees that these 3 points, A prime, B prime, C prime, will be along the same straight line. Not of course the same straight line as this, some other straight line, but straight line nonetheless. Now, different stars, although they are acceleration free, they can very well have different velocities. They can move in different directions, which is why our straight line here is not parallel to the straight line. They can also move with different velocities. But what is critically important here is once we have established a definition of time using our star S1's motion, I no longer have the freedom to change time any longer. But now what observation will tell us is that the gap between A prime and B prime will be exactly the same as the gap between B prime and C prime. In other words, S1 is traveling with equal velocity in the first interval as the second interval. This is a rather trivial thing to say because this is exactly dependent on how you defined time. Velocities had to be equal. There was no option there. However, once we use that definition of time, that will also render the velocity of star S2 between A prime to B prime equal to that between B prime to C prime. This is a non-trivial and testable prediction that Newton's first law is making. Not only is AB equal to BC, which of course was by design, A prime B prime also has to be equal to B prime C prime. And this is something which does not follow from the definition at all. And not only will this hold for the distant star S2, it will hold for all other distant stars as well. So at the end of the day, what Newton's first law really guarantees is the following. There must exist at least one observer for whom we can define time in such a way. The way is of course using one of the moving distant stars as we described, that all distant stars are rendered acceleration free. In other words, Newton's first law is not just an existence statement for inertial observers. It actually goes a lot deeper than that. It makes it possible for us to define a time for that observer. And of course, once we have defined time for one inertial observer, we already know how time has to be defined for all other inertial observers. But what is important is Newton's first law guarantees for you that such a definition of time is at all possible. This, let me stress once again, is not a matter of just defining time. Defining time would have ensured that the star that you are using to define time would be acceleration free. But there was no guarantee that other distant stars would also be acceleration free. That they are is the non-trivial statement which Newton's first law is making about the nature of the universe. So not just defining inertial observers, not even just the existence of inertial observers, Newton's first law goes to the very heart of the concept of time itself. Not for nothing has this been called one of the greatest innovations ever made by the human mind. Hope you enjoyed our journey into that.